So I think now we're all set to go. To move this, then I can present it as a slideshow. So the talk today is on a certain technique from data analytics called principal components analysis. How it's going to work is we shall I'll roughly go through some slides trying to explain how it works, the concept or the principles behind it. And then we shall do some live demonstration of how it works in R. Now, there is some, the folders and the code that I have used for this are available in a Google Drive. So what I'm going to do, I'm going to post the link in the chat. Where is that? There. I'm going to post the link in the chat, then you can download the folder to your computer if you have your computer ready. Or if you're using your computer, you can download it. And when we are running the code, you can also try to run it on your end. Otherwise, you could just see what is going on and then run it later in your own time. So now I'll go back to the presentation. So if you have any questions during the presentation, I think maybe you could raise your hand. Someone will probably let me know. And then you can ask your question. I think it's better if it's interactive. If there's any explanation you need midway, you just let me know, then we clear it up as we proceed. So let's see how much we can get done. We'll try to keep it within the hour. Did someone raise a hand? I can see Leon.
Yes, doctor.
Not. Yes.
So, I can't see the link. Or you are going to post it later?
Okay, let me double check. Maybe I sent it to a specific person instead of.
Yes, I'm trying to copy it and I'll post it. I'll post it.
Okay. So it will be posted.
Okay, thanks.
Okay. Good. So let's get started. So so this is the basic structure of the talk. We'll cover the basics of principal component analysis, then covers food science application in detail, and then briefly cover 2 or 3 more applications on the slides. Then we'll cover them in more detail when working in R. So basically, this should be principal, not, that should be PAL, not PLE. I think I need to correct that spelling. So it's a technique that picks some set of variables. If you have a multivariate data set which has a lot of variables, and you can transform them now into another smaller, into a set of uncorrelated variables, and which are now ordered in order of importance. And
your presentation is not visible.
Yeah.
Pardon?
The presentation is not visible.
I have shared. Why has it?
I think you have to reshare.
Yes.
Visible at the beginning, but now it.
Yeah, I'm doing it again. Thank you for the. Okay, just give me a minute. I set up this. It should work well. I don't know why it's misbehaving. I'll reopen this. Okay. Now it should work. So see the slides now?
Yes, yes.
Yes, now.
Just better now.
Thank you. Good. So so I'll start again. So principal components analysis is basically a multivariate statistical technique that helps you to reduce the dimensionality of your data. When you have too many variables, sometimes it's very difficult to interpret them and also difficult to figure out which ones are more important. And principal components analysis provides us a way to reduce the dimension and work with fewer variables, and not only work with fewer variables, but know exactly how much of the information is retained by the few variables that we pick. So it's a fairly old technique, started in 1901 and further developed in 1933. So it's well established with a lot of material about it existing. With the advent of the computers now, there's a lot more being done. So these are some of the things that you can achieve with principal components analysis. It helps you to simplify the description and also to visualize the data, extract some features, filter out noise, and make it easier to interpret the data. Some of this we shall see as we go along. So basically, the structure of the data you work with will be in this form. This would be your raw data, your original data, with k variables, where k is some integer. They can be as many as 4, they can be as many as 100 variables. And then you have the cases. So we'll work with a situation where we have n cases. So for instance, if you are in class, you could take your first case as a student, and the variables would be grades in the different subjects, and so on. Something like that. So all these are cases, or if you like, experiments, depending on what you're dealing with. So there will be n cases or n experiments and k measurements or k variables. That's how the data is set up initially. So now this original data usually will have some highly correlated variables which may represent the same thing. So what we do is we transform the data into another set of variables, which we call y1, y2 up to yk. And then the transformation will be linear combinations of this original data. So each of these y1, y2 contains information about all the variables that are in the original data set. But now they are weighted to show their importance within each of the new variables. These new variables are what we call the principal components. So once you do the transformation, you will have a new data set, which is exactly the same size as the old one, the original one. But now the data will be transformed. This will be your new data. The difference now is that these variables are ordered in order of importance. In other words, the y1 will be more important than y2. I'll explain what I mean by important in a short while. Or basically what important means is that y1 explains more variation in the original data than y2 and so on. So they keep decreasing in the amount of information they hold about the original data. So far at this point, we still haven't reduced the dimension because we still have the same number of variables as we had in the beginning. But because of the ordering that we have imposed on the data, we can choose to pick as many variables as we find necessary to retain a certain amount of information. So this simply repeats what I've said. And also one more thing, these new variables are uncorrelated. These coefficients are picked, these A1s, the A2 and so on, they are picked so that the new variables are uncorrelated. And this is what we were talking about importance. The variance of each is getting smaller as you move further. So how you can put it in matrix form. The original data set, we can call it X. Think of it as a matrix X. And then T is a set of, then it would be the Y1, Y2s up to YK. And then V would be the matrix, the weightings that were done during the transform. There are techniques to obtain matrix V. We shall not go into the techniques, but it's an orthogonal matrix. Orthogonal also has a, it may not be so important now, but it's an orthogonal matrix. And basically it's if in a nutshell, it's what you obtain V through the eigen decomposition of the correlation matrix of these original variables, X1 up to Xk. Some cases they use a covariance matrix, but most of the time the correlation matrix makes more sense because the variables are scaled, and therefore it makes it easier to compare variables that have huge disparities in measurements. So through that process, you obtain these eigenvalues, and these eigenvalues are just the variances we were referring to. Eigenvalues is just a big word, but basically it's these values, the variances for each of the new transformed variables. So the key thing is this: you have a new set of variables T obtained from the old set, and using this V to transform the variables. And this V can be obtained through some process called singular value decomposition. But for us, the computer will do that for us. V will be found by the computer, and we will not have to worry about it. So the new data in this T are usually called scores, and then the elements in V are called loadings. So we shall see an example where we can put something concrete onto this. So because of usually sometimes you have a lot of disparities in terms of magnitudes in the variables, we usually scale the data to make it have a mean of 0 and standard deviation of 1 so that they're easily comparable. Some of these I've already said because the T just is exactly the same size. And but now the difference is that the variables in T are now ordered in order of decreasing importance, and then that means we can select only a few of them and still retain a reasonable amount of information, and then be able to use those to represent our data better. So for our case, since our interest is mostly visualization, we will just work with the first two principal components. Depending on what you're doing, you may need more, but for our case, since we'll be focusing mostly on visualization, we just need the first two. And when you, with the first two now, you're able to plot your data on a Cartesian plane, and you'll be able to extract any features or patterns, or even clusters, if there are any clusters in the group. So how you determine how many variables to retain is working out the proportion of variance that is explained by the variables. So if the first two explain a reasonable amount of variance in the original data, you can just keep the first two, which is what we shall do. So usually there's you can draw a scriptplot. A scriptplot will show the different variables, the different principal components and the amount of variance they explain. And through that, you can easily see how many variables to keep. So this is what I said. In our case, we shall just be working with the first two. And there are situations where this technique is also not so useful, especially when the eigenvalues are mostly equal. So there's no quick drop in eigenvalues or the variances as you go through the variables. Then in such a case, then the principal components analysis may not be very useful. The other cases also, when they are nonlinear relationships, then you may have trouble with the principal components analysis. But for now, we shall assume all the assumptions that favor principal components analysis are at play. So the software we shall use is R, and we'll use an integrated development environment called RStudio to run out the analysis. R is good because the good thing about R is it's free. You should download R and RStudio. We have the for downloading RStudio. I would like to go to I hope you will hear. Hello?
Yes,
We
Dr.
can hear you.
Your sound is
Okay.
breaking though. You're breaking a bit.
I don't know why my. Can you hear me now properly?
Yes, it's clear, but at some point we
Yes, we
somehow
do.
lose you.
We can hear you.
Yeah.
Yeah, we can.
So if at any point I'm not clear, maybe someone should say so. So that we check and see if we can.
All right.
Good. So I don't know if I need to leave this for a minute or so that people can take the details.
Can I ask a question?
Yes.
All right, just to understand this better. So PCA is used to you're using new variables from your transform data so that you can do analysis on the new transform data, correct?
You may, in our case, we are just going to, yes, you can do analysis on the new transform data, but in our case, mostly what we are going to do is use it to visualize patterns in the data.
Okay.
So beyond that, you can use them to run other models like classification models and so on.
Okay, all right.
Yes.
So you mentioned
So that's
about
possible.
eigenvalues, and you've said that if they are equal or it's almost equal, then PCA may not be very useful. So does it mean that you have to first calculate the eigenvalues before you do further visualization?
Yes. So the reason they will not be useful is if you have if they're all equal, then all the new variables you have seem to all have equal importance. So you may not be able to cut off any easily.
Okay. Makes
Or
sense.
if you are to cut off, you may have to cut off so many. You may need so many to be able to retain the desired amount of variation that you want to retain.
All right.
Yeah. So
Thank you.
now, unfortunately, there's a lot of detail about this that I have left out, mathematical detail, likely because I wanted to reach out to a wide audience. So later on, if there's interest, we can work out a presentation which now covers the technical aspects.
There's a hand from Leon.
Yes, Leon.
Yes, doctor.
Yes.
I have a curiosity question. You are talking about the eigenvalues, and you are talking also about the SVD, singular value decomposition. So I am wondering if there we have to consider eigenvalues or singular values.
The singular values are useful. We will consider eigenvalues because the eigenvalues are actually the variances of the new transformed variables. So the eigenvalues, in the process of running the singular value decomposition of the what do you call it? The covariance matrix or the correlation matrix, you will get some eigenvectors. Those eigenvectors are the variances of the
somehow,
new
but
transformed variables. Yes?
Somehow, but you know,
I mean, eigenvalues, sorry.
Yeah, you are talking about eigenvalues, and because we are talking about SVD, because correlation variances sometimes are not square metrics. Then you transform them to get the singular values and and principal components.
You will need both the eigenvalues of the covariance matrix to be able to obtain the eigenvectors, and then the square roots of the eigenvalues will give you the singular values. So you need both.
Okay, thanks.
Yeah, but I'm avoiding the mathematical side for the sake of a larger audience. But anyway, if you have a question, you can always ask. Yeah.
Okay.
Yeah. So we will look at a practical example from food science. Some of this I don't understand totally, but I understand the mathematics side of it. The basic idea here is that you have 4 different types of flour made from banana pulp and banana peel. So there's the green ones and the ripe ones. So you have green banana, so you have green banana peel and so on, and ripe possibilities. They take samples from several of each, and these are the things they measure. There's the pH, there's total soluble solid. Some of this, maybe if there's someone in food science in the audience, they can help with understanding what the chemicals mean. There's water holding capacity and oil holding capacity at different temperatures. There's some variables which measure color, and this L star, A star, B star. Then there's back extrusion force and the viscosity. So these are taken. These are several measurements taken on all the banana varieties. Okay. So so we have the last part is just a repeat. They are the 4 types. They are coded as GPE for green peel, RPE for ripe peel, green pulp is GPU, and RPE is for ripe pulp. So this shows a small portion of the data. So you can see the cases are along the side here, and then the variables are up here. The columns represent the variables. So they are grouped. This group is a variable, the categorical variable that shows the type of flour being used. And then these are the measurements taken from the different flours. So this one just, the first 4 are the green peel flour variety. There are more that come towards the end. There are a total of 48. I think they took 12 of each. So a total of 48. Now the next, here we measure the variances in the original data. And you can see there's a lot of disparities between the variances. Some are very large variances, some are really small. So this is why we use we have to scale the data so that it has mean 0 and variance 1 each variable. Then it makes them comparable. Otherwise, the importance of these variables, which have large values for variances, will be exaggerated. So the scaling helps to bring down that exaggeration. So one way to visualize this multivariate data is to use scatter plots, these pairwise scatter plots. So the only problem you have with that is that if there are too many, because there are situations where you can have as many as 100 variables, and you'd have to go through so many scatter plots. So this is why you need to figure out a way to reduce the dimension. So this is only for the first 4 variables. So and already you can see some patterns. The only problem is that now you can't tell which variable is the most important and which one is less important. But principal components analysis enables you to figure that out. So here you might think there are too many and want to leave out some, but you have no criteria for knocking out any of the variables yet. So that's the problem you have at hand.
Hi,
So-
Doc. Allow me to interrupt. There's a question also from Daisy on the chat.
Yes,
He's asking whether the main use of PCA is to identify the most important variable and also to aid in selecting them. That's her question.
I don't know how to put it. No, what you do is not to identify the most important variable, but to transform the variables into a new set of variables that can be ordered in order of importance in terms of the variance that they explain. And therefore you can pick, say, like if the first two represent a reasonable amount of variance, then you can just use those two to represent your data. And you can be able to visualize it graphically. And if there are any patterns that are available in the data, you'll be able to see them. Otherwise, if you're working with 100 variables, it's difficult to graph them in one graph. But if you can collect the information in those 100 variables and get them into two variables, which represent a reasonable amount of variation, then you can comfortably draw them in a two-dimensional plot and comfortably know that you have what you have is sufficient. As we go through the examples, if you have many variables, you have to draw too many of these pairwise scatter plots. Now, another thing that you look at is the reason you need to reduce dimension is that a lot of the variables usually may be highly correlated. And the variables that are highly correlated probably represent the same thing. So they may be identifying a certain feature in the population, and principal component analysis will be able to bring them together and reduce the number, try to sort of lump the correlated variables together into one feature. So if you look at this, this is a way to visualize the correlation among the different variables. And you can see we have some high ones as well. And that is a good thing for us because principal components analysis tries to solve this problem of high correlations among the variables. So when you run the principal components analysis, here you have the, you can get some summary of it. The summary will give you, this may be small, but I hope you can see it. You have standard deviations for each principal component. So this comp1, comp2 are the y1, y2, all the way up to y13. Initially, we had 13 variables, so we get 13 principal components in reducing, in order of reducing importance. So you can see the standard deviation of each principal components in the second row. And the first one is larger than the second one is larger than the third, and so on. Then it also shows the proportion of variance that is explained by each component. The first one explains about 44%. The next one about 30%, and so on. So with the first two already, you have 70% of the variation explained. And that might be sufficient for your purposes. If you need more, you can go up to the third, which explain collectively up to the third, you have explained about 87% of the variation of the data. So many times that is more than sufficient for work. And that means you can work with only 3 variables instead of 4. I mean, instead of 13, not 4. So this is a script plot which also can help you visualize the variances in each principal component. So you can see the first one has more variance, gets smaller and smaller as you go along. And you can see the first 3 represent most of the variation. The rest represent very little. So again, in this case, we can see the first 3 may be sufficient for any further analysis that one may have. So this will be mostly our criteria we use for determining how many principal components we retain. We just look at the script plot and see Usually, but by and large, we shall just pick the first two because what we want to do is visualization. So you can extract the matrix. The matrix that we said is called V. You can extract it using these loadings. The principal components object normally has some extra variable here called loadings. So you can extract it. So this gives you the matrix V, which is orthogonal matrix. This one also tries to show you, you have the variables on the left-hand side here and the components at the top. So these are the coefficients that you use to transform the original variables. So although in our case, they are not really the original, they will be the scaled variables, the ones we use to transform the scaled variables. So it shows you, for instance, in principal components, there's this L. I'll just pick out the ones that have high values for coefficients. We have this, there are quite a number that have high values. So it seems to be a general component. Component 2 seems to pick TSS as a high value. So it's important for this component. There's also viscosity, seems to have a high value. It's important for this component. So this is basically the coefficients that are used to transform the scale data to get the
Hi, Dr. We are losing you.
the new variable.
Please check on your audio.
Hear me?
You're breaking.
The connection really is very poor. No.
I don't know, it shows full connection on my end, so I don't know what,
So now
why
it is
picked on
okay.
today to behave like it. It is okay now.
Yeah. It is okay now.
You can still see the screen?
Yes, we do.
Can you see the screen?
Yes, we do.
Okay, because on my end, okay, good. So now this is a new data set after transformation, and this is now what we can use to visualize our data. So we can plot these first two variables, and that will enable us to see any patterns that are in the data. So the way it is done, since the transformation is orthogonal, usually points that are close in the original data still remain close in the transformed data, and those that are far apart, most of the time will remain far apart in the transformed data. So if there are any patterns that are in the original data, they will be amplified in this reduced set of data. So when you plot those first two variables, which are the first and second principal components, you clearly see that there is a clear pattern. You're able to separate the ripe pulp, the ripe peel, they're all perfectly grouped. And that means these variables can account for that, those patterns that are in the original data. So you can also notice that the principal components, the first principal component is able to separate, it's largely separating the green from the ripe, because the green ones seem to score towards the positive end, the ripe ones score towards the lower end, below zero. And then the second principal component seems to be able to separate the ripe, between the ripe and the peel. The two ripes are well separated. So
Dr.
Yes?
We are not able to see the plots. We are still in the scores. I think you're talking about the plots, if I'm not wrong.
Okay, let me do this. I will stop sharing, then reshare the screen again. I'm not sure what is causing the problem. Let me reshare. So are we? How is it on your end now?
It's better. It's
Better.
okay.
Okay.
I don't know whether you can
So-
take some time to look at the questions as we proceed, or we will allocate some time.
So, but
it
maybe,
will
Doctor,
interfere
can
with
you
the-
move it? Can
it
you
will
move
interfere
to
with
the
the presentation.
graphics?
Yes. Can you see the graphics now?
I can't. It is okay now.
Now you can see the graphics.
Yes.
Good. So I'll just go back to the table again. We are plotting these first two principal components to be able to visualize the data. And we saw that the first two will retain a reasonable amount of variance. About 74% of the variation is retained by the first two. So we don't lose much by keeping just the first two. And by using those, we're able to see the patterns. We can clearly separate the different flower varieties. So this means you can use these variables for classification of these flower varieties. So if you get a new unknown flower and you want to classify it, you can take the same measurement on it and project it onto the first two principal components. Like now, this is a new measurement whose classification is unknown. But when you project it onto the graph, we can see it lands squarely on green peel. This red spot is where it has been projected. So we can now classify the unknown flower as this green peel variety. So that's one thing you can use it for prediction or classification. I hope that makes sense. There's still a lot of technical stuff that I have to leave out. And this is biplots. Biplots also just shows the same patterns that we had represent the variables, score positively on the first principal, then the ones are this facing towards the left. And the ones that are closer to the x-axis are the ones that are more correlated to the, or more important to the first principal components. The ones that are closer to the y-axis are the ones that are more important to the second principal components. But basically, the idea is you've been able to show that with just two of your new variables, you're able to see the patterns of classification. And it proves that you can classify your flowers using these variables. Now, this turns out to be fairly perfect separation, but this doesn't always happen. There are times when you have a bit of overlap here and there. So at least we are through with one application. Maybe it's time to celebrate our small win and move on. Now the next application will not be detailed on the slides. It will just show the final plot. So this was some data from there's some study from Latin America where they had some questions sent out to people, and they were measuring sort of the attitude towards democracy, whether they trust the institutions, whether they can justify coups, whether they justify shutdown of Congress and so on. And after some analysis, 3 distinct groups were isolated. You can see the pattern that came out after. There were a total of 11 variables used in this analysis, but we were able to reduce that to just 3 features. So as a political scientist, this can be useful. You can try to classify the population into 3 different type of political attitudes and so on. So that's another application. Again, no details for this for now. Maybe this one now is from the health sciences. This was some 30 numerical variables. They took some images of some breast cancer cells, I think, and took 30 different measurements from them. And again, you can see out of 30, we're able to just work with 2 and still see the patterns. Here, the red ones show the benign tumors, and the black ones show the malignant tumors. So again, it shows that just by using these 30 variables, it should be possible to classify or do some diagnosis on the tumors. The links to this data, I think, should be available in the R file. So this last one is a outlier detection. This is an image from this NASA page. There is a, if you look in the picture, there is a small, it may not be easy to see on your end, but it's a small pin, metal pin here in the picture, which may not be easy to see with the naked eye. But after running some PCA, you can pick the first two principal components, and you will see that the first one picks out the texture. So you can see the sand clearly in the first one. And the second one picks out the darker colors. But now you can't see the sand very clearly in this one. It's smoother, so it doesn't pick up the texture. Though now the pin can now be spotted as a small dark spot where I've put the white square. There is a small dark spot which can now help you realize that there was a pin in the picture, which you may not have seen before if you didn't have the separation. So the last one is a geochemical example. I can't remember how many variables there were, but now they've been reduced to two principal components. What they were measuring is they had two formations, I think, and they were taking a lot of measurements on this limestone. And clearly we can see a separation between the Hermitage and the Carter's formation by just looking at the two. Now, if you are looking at all the variables, it may not be possible to visualize them like this. So these are some of the sources of the work I've presented. And
Thanks, Daktari.
that
As
one-
you take a pause there, I don't know whether you can address some of the
we'll have
chat. Hi, sorry,
Okay,
I was
let
saying if you
me-
can address some of the chats as we take a pause on the references.
I can't. Okay. Maybe is it possible for you to read out the questions?
Okay, thanks. There was one from Kenneth.
Yes.
He was asking if does PCA achieve the same objective as multicollinearity tests? And there's a guidance has been given there by one of the participants. Sorry. Maybe you can respond also just to confirm whether he's been answered correctly.
So anyway, I'll try. I can check. If I remove this from the screen, I can go back to the Zoom and check the chat then. So I'll stop sharing so that I can go back to the chat.
It's okay.
Okay, there are many. Oh. So
The last question we
multicollinearity.
answered, yes, there.
Now, multicollinearity is a concept, is basically where you have a large set of variables and a number of them are highly correlated. So normally when you have these highly correlated variables, they probably represent one feature. And that becomes a problem, especially when you're dealing with multiple regression. So usually we prefer that if they represent the same thing, then the model is not very reliable. If you have too many variables that are highly correlated, the model becomes unreliable. What principal components analysis does is it transforms your variables into a new set of variables which are uncorrelated. That's what it does. So I'm not sure what it means by multicollinearity test. multicollinearity is simply to check whether the variables are correlated, to test whether they are correlated. So that simply tells you whether PCA will help you more. If they're highly correlated, then PCA will be useful, because then it will be able to reduce your features into fewer. The variables that are highly correlated will be lumped into one feature usually. So I avoided the details. So someone talks of prior pre-processing and so on. I could not cover all the details of data analysis in the talk, because there really isn't time. It's a very huge topic, this one. So I just wanted to focus on how you apply principal components analysis. So someone is asking, how do the loadings direct us to transform the data? Now, this will force me to start doing the equations on the... I was trying to avoid this. So basically, the loadings are in the matrix V. We use that matrix V, which I had in the presentation, to transform the original data into the scores. The scores are the matrix that I call T in the presentation. I don't know if it would be helpful. It works better if yeah. Now, Omichemi, I thought I explained this. The variables that are closer to the principal component usually show that they are more important in that to that principal component, or that feature, or the feature that the principal component represents. That's Omichemi's question. I hope it's answered. So yes, it can be used in prediction models, and if you allow me to go to the R presentation, you can see some demonstration where we do some classification and a bit of prediction. Already we did some prediction with the banana, new data on the banana flower, and we were able to predict which type of banana flower it would be in the presentation. There are quite many. So I don't think I will cover the noising in this presentation, but we could arrange to have another talk which covers the denoising. A simple example would be when you're doing image compression, and images normally have a lot of noise in them. So you can compress it by just keeping the important signals. PCA can help with that. In particular, singular value decomposition can help with that. So I will make arrangements to send this presentation to I think the link that was shared earlier, the link to the Google Drive also has the presentation. I have shared the link again. It also has the data and the code. Now, given the time, we were planning to work only up to 11, but we have taken longer than I expected. I think there were many questions. So let me try to run through the R application. We may not be able to do all of them. We might pick one or two, and then the rest you can just run them in your own time.
Just before we move to the R application, please.
Yes.
I asked two questions that were not adequately answered. Maybe you can just reiterate your response.
Yes.
On what is the implication of the negative loadings? That is one. Then two, can we use the PC loadings of nonlinear data into classification models, the ANN? Can it be fed into the ANN for classification?
So the other techniques for that handle nonlinear data better than PCA. So if you have nonlinear data, maybe one way to fix it is to transform the data so that you can use PCA on the data. And then the other thing is to work on other dimensionality reduction techniques that work better with nonlinear data. So basically if you look, let me put back the presentation so that I can use it to explain this, the second question about the negative loadings. Now, basically, it means, let me share the screen again. Without the equation, I don't want to write on the board, so I'll just use the. So these values, this small a with subscripts are the loading, right? Can you see my screen? So if one of these loadings is negative, it means and hopefully it depends on now your variables. If your variables are all positive variables, if any of the loadings are negative, it means they reduce the value of your principal component. But the standardization is what gives you those negatives and the positives. So let's get so basically these principal components, if you move towards this direction, you are moving towards the right pill. And what you really need to look at is not so much the sign, but the magnitude of the loading, right? If a magnitude is high, then it means it's important. It might be negative, but important. So in the opposite direction, but important to that principal component. And again, if the magnitude is high towards the other end, it's positive, yes, but the magnitude is large, means it's still important. So what you really need to look at is the magnitude, not so much the sign in terms of importance. Hopefully that answers your question, or at least 70% of your question.
Thank you.
Okay, so I'll try to run through the R quickly so that those who had planned to do something else can be able to go. So the same R files are also in the Google Drive. If you wish to run them on your end, you should be able to. Can you see the screen?
Yes.
Oh, okay. So this is a food science example that we saw on the one that was covered in detail in the slides. So I'll just run through the code and try to explain what it does. So the first thing is to load the data set. And then we can look at the first few lines, first few cases for the data set. We looked at the first four actually. So this shows you how the structure of the data set. You have a group variable here, which shows you the type of banana peel, whether it's a green or ripe, and also banana pulp. There are 48 in total, but I've picked only the first four. If you want to view we can get a spreadsheet here that will give us a better view of the data. Let me just run it. So this gives you a better view of the data. And now you can see the other varieties as well. We have the ripe and the green peel. Then as you go further down, you will see we have the green pulp and the ripe pulp flower varieties. So I will close that. Okay. So the next thing we did was to pick the numerical variables, because the principal components analysis will work on the numerical variables. So this first variable for the group will be left out at this point. We can compute the variance for each of the variables and draw a bar plot. And this shows you the disparities between the variances for the different variables, which necessitates the scaling so that they are comparable. So we need this library. We load this library called Psych so that we can draw the pairwise scatter plots. This first drawing is not, you don't need the Psych library to draw that. But it also quickly shows you that they are colored by the banana variety. And you can see already there's some patterns that are showing up even before you do the PCA. So you can pick to show if any patterns are in any one of the variables. You can draw a histogram. Now for this variable TSS, we can draw a histogram and see what it looks like. And already this multimodal nature of the histogram tells you that there must be some clusters within the data. But one variable alone may not be sufficient, may not cover all the variation that you need. That gives you an idea. So these pairs.panels, if I run that now, this line number 30, this one gives me a better it gives me a better representation with more detail. So we have you can see the different patterns, but we also have the histograms already built in. And you can clearly see the multimodal nature of the histogram, showing that there must be some clusters within the data. It also gives you the correlations if you want to look at the correlations, but we only picked the first 4. There are 13 variables. We did the drawings for just the first 4. Now the next part is we compute the correlations. So this gives you a matrix of correlations, which is not very easy to look at. So we shall use this package and this command to have a better visualization using the diagram. So the blue, as you go towards the blue, you have high positive correlations. As you go higher and higher, and as you go lower and lower, you have it looks like brown to me. The different shades of brown gives you the different values of correlation. The darker the brown, the higher and negative the correlation. And for blue, it's positive. So here you can quickly see some high correlations with the darker. This is easier to visualize than this other matrix of correlations. So the component analysis should be useful. Principal component analysis, and then if I run a summary on the object, I get these standard deviations and the proportion of variance that each principal component represents. So that's what we have down here. And cumulatively, you can see. Pardon? Did someone speak?
Just proceed.
Okay. So if you want to pull out the standard deviations alone, you can use this. One of the attributes for this object is a standard deviation. So you can just pull it out using this command on line number 48. So that gives us the standard deviations, or what Leon was calling the singular values. Now the variances would be the squares of the standard deviation. So we obtain the variances by just squaring the standard deviations. And then there's something I forgot to run up here. And that's a scree plot. So this scree plot is the one that shows us the variances for each of the principal components, and they keep reducing as you go down. Now, one way to visualize these variances for each of the principal components is to use a scree plot. The other one is just to have a plot of the cumulative variances, and then you can easily see your cutoff if you wanted to determine how much variation you want to retain. So that's what we are going to do next. So this gives the cumulative variance for each principal component. So for instance, up to the third principal component, you're almost covering 90% of the variation. And that tells you that in this case, principal components will be very useful. So we clear the graphs there. You can also obtain these loadings attributes. And here they are. I will not go into the details of the loadings, but this is how you obtain them. Now, the transformed data is what we call the scores, and you can extract it using this scores attribute. And this gives you the transformed data, which we call T. And then at the next point, we can plot the scores of the first principal components. Again, you can see there's some separation between the green. I think these first two are the green ones. They score more on the positive side. The ripe ones seem to score more on the negative side. This one now is a plot of the first two principal components. This is what we saw in the slides with the separation. So the rest of the code is just labeling the different types of flower varieties. And now they are labeled. So again, this separation is perfect, but doesn't always happen like this. So we can run the same using this ggplot, and we get a different looking diagram with a legend. We could have put a legend also in the original one, but this is just the same as what we drew earlier, but now using a different package, which seems to give a better looking graph. So now if you have a new data point, we may want to predict which type of fly it is. So that's what we are doing from line number 88. So we create a new data point. We project it onto the first two principal components. And we now, after the projection, we can plot it on the graph. I'm redrawing the graph, then now I can add the new point. You can see the new point is plotted among this green peel variety. And therefore we can conclude that the new unknown flower that we had should be from this variety. And this gives you the biplot. So the biplot shows you the variables and how important they are to the principal components. So the ones that closer to the horizontal, more important to the first principal component. So if it's someone from food science, they might pull out does it present and so on. So you classify the certain set of feature that comprises a number of variables, and this also measuring another feature. Now I didn't know how to classify them myself because they that my area was just the mathematics side. So the next example is from the political science field. Unless there are questions, no questions on this one. So for this one, there's this Latin American public opinion project, LAPOP, from the Vanderbilt University. I think they I have given a link to the questionnaire that was used for this. The questionnaire, I think, is in Spanish or one of those languages. So I don't think you can understand it, but the data was translated in English, but the questionnaire on that site gives you the full questionnaire of the data that was collected. So only 11 variables were picked from there for running this data. So I'll load the data. Then now there were total of a little over 7,000 cases. When you're trying to draw the graphs, if you work with too many cases, it can be a bit problematic. So what we have done is taken a smaller sample from the 7,000. I think there were 10 countries. So picked this line of code from 136 to 138, picks 100, a sample of size 100 from each country, so that we can have a smaller sample for our visualization purposes. If there are too many, the graphs are usually too crowded, then it's difficult to interpret them. So we run the sample, and then we can create a new variable, or maybe we can, it may be good to look at the data, because we have not seen what the data looks like. It may make more sense if we look at the data. So these are the countries along here. You can see there are 7,655 entries. Then we have there are 14 columns, so 13 variables. Is this whether you support demonstrations, is vote opposed, whether you oppose the votes? I think there was a vote. There's some details about this. Maybe I should get them before I talk. Then a number of the questions were checking on the trust of the various institutions, democratic institutions. We have these two, I think they are asking people if they can justify a coup or a shutdown of Congress. Some of this may not make sense to our system because we don't have these structures, but it will serve the purpose. So all these were on a scale of 1 to 7. The questions were being asked on a scale of 1 to 7. Yeah. So in the code, we pick one of the variables, which is a trust in elections, and we get the mean and add it as a new variable to the data frame. And that gives us the average by country. The average is done by country. So in the next plot, we shall plot the average in that particular variable, trust in elections, as a vertical line. So this plots just this one variable only, trust in elections by country. And you can see that this Uruguay seems to have a higher trust in the elections because the average is quite high. It's above 5. Seems to be the highest. The others seem to be roughly around 5 or just below 5 from a scale of 1 to 7. So since to run the principal component analysis, we have to remove the categorical variable. We just want to keep the numerical variable. The country variable is not quit, and we have a new which is scaled, and we also meet. So that's how we have chosen to treat. But in this case, we don't have too many missing, so we can omit. So we can run the correlation and also visualize it. So this shows the correlation. These ones are not as high as for the previous example, but they're high enough, 0.5, 0.4. They're reasonably high correlations to help us, to make us think that we can lump. You can do further tests to see the significance of the correlations. That is also possible. I did not do that in this case. So we ran the principal components analysis and do the summary. The summary, we have set it to give us the loadings. And when you look at the loadings now, you can see in the first component, it loads heavily, mostly on the trust variables. The second component loads heavily on these to justify coups and justify Congress shutdown. So this gives you a different type of attitude. And then the last one loads heavily on the vote opposers. Also, it gives you a group with a different attitude. Now, if you look at the cumulative proportion of variance, up to the third component, we have only 52% of the variation explained. But up to the second one, we have only 43% of the proportion explained. That may not be a bad thing. We can still try to draw a visualization. It may still pull out the patterns that we are looking for. The next bunch of code largely looks at the eigenvalues. So this is a script plot. It shows you the proportion of variance explained by each component. There is this library that you need for that. This library called FactorExtra. You have to install that library, the package, and load it to be able to run this. So this is still the same thing, another script plot with different settings. And this one is now the biplot. And from the biplot already, you can now see there are 3 different groupings. Remember, when we looked at the loadings, it seems to suggest that there are 3 different groupings, and the biplot also seems to show the same. So you can see this justify Congress and Congress shutdown and the coup, people who can support the coups or shutdown are closely linked. Then there's vote opposers seem to be on their own. Then we have these trust variables. These are the people who maybe trust the institutions. They seem to be highly correlated. So it gives you roughly 3 different attitudes, political attitudes. I will skip this part in the interest of time. Okay, then I think I can run this. These are still so this part just creates a new index. I will skip the index part. It creates an index to measure the political attitude. So since I did not say much about creation of indices in the talk, I think I'll run it, but I will not spend too much time on this. Then you can also try to see how the index fares by country, plot it separately for each country. So now we can pick out the scores and plot the first 2 scores on the first 2 principal components, and we can see the pattern comes out again clearly for the 3 political attitudes. They're separated largely on the second principal component. There's a widespread on the first principal component, and therefore they probably there are some clusters in the component on the clusters that are determined by the first principal component are seem to be clearly separated. So you can also try to visualize the loadings using using bar plots instead of the tables. So we'll put the loadings on the first three principal components. And you can see for the first principal components, we have heavy loadings on the trust. This may not be so visible. I don't know if I zoom whether you still see it. So this first principal component seems to pick out the variables that measure the trust in the institutions. The second one seems to pick out the variables that check whether individuals justify coups or Congress shutdowns. The third one seems to pick up the vote opposers. So this can give you three different political attitudes, and you can use that to analyze your population. I think the political science people may be able to explain that better than me. So we can now try to use some clustering algorithms. Again, I didn't explain anything about clustering, but I'll just run this, and then you'll be able to see. So if you try to find the clusters, this one didn't do so well. I don't know what went wrong there. So this tried to find the clusters along the horizontal axis. I think there's something I did wrong. There should be about 3 of them, but it's doing a lot of overlap. So I will not try to correct that now. Then the next thing is we try to group. You see, along the second principal components, there seems to be some natural groupings. So we'll try to do that grouping in the data, then try to find the same clusters using some linear discriminant analysis. Oh, I've done a mistake. So this code here simply groups them into these 3 clusters that appear on the screen. And then we set up a data frame, and then we run this linear discriminant analysis. Linear discriminant analysis is some supervised kind of learning that I will not go into details again, but we can check the accuracy of the classification using the linear discriminant analysis. It's about 99% the classification if you use that class, if you use those clusters. But that is expected because we could see. So if you get a new data point, you can easily classify them in one of these clusters using that this linear discriminant analysis. So this histogram shows you how good the classification is because there's a clear separation. Now this running these ones is not sufficient. Many times you have to do a lot of cross-validation for you to check that your classifications actually are stable. So this shows the classification using the clusters that seem to be determined by the second principal component. So I think that I will now try to move on to the health. I hope there are no questions on that.
I'm not seeing any question on the chat unless somebody has a question they may want to raise their hand, but you can proceed.
Okay, so the next one is showing the data on the breast cancer. So this one, they say they've got the features from a digitized image of the fine needle aspirate. I have no idea what that is, but the medicine guys might have an idea. The fine needle aspirate of a breast mass. So I've also indicated the source of the data. There's a website here where you can find the data and download it if you wish, but it's also in the folder I shared. So we read the data, variable that you So to view the data, you can see it in the spreadsheet. So this is how the data looks like. There are two types of tumor. There's the malignant type, and then there's the benign. They're all mixed up. And then there are all these measurements taken. There are about 30 numerical measurements that are taken on each sample. And then the sample is already classified as either benign or malignant. But now you see the 30 variables are too many to be able to graph in 2 dimensions or even 3 dimensions. So we use principal components analysis to reduce that dimension and try to see if we can determine, be able to predict which, given some new data on a tumor, to predict if it is benign or malignant. So I will run through this quickly again. So this gives us a scatter plots for a few of the variables. There are 30, so I didn't list all of them. These are about 7, I think. But again, already you can see the patterns. These red ones are the benign tumors. That's how I've clustered them, colored them so that they can be. So there seems to be some clustering already, and that's a good thing for us. So we keep running. On one of the variables, you can clearly see there's a difference between the benign and malignant tumor. So again, that tells us that there might be some variables that will help us do some clustering. So we scale the data, then run the principal components analysis, do a summary. I will not look at the loadings again. I want to now. This is the script plot. So the first dimension shows picks up 44% of the data of the variation. The second dimension picks up 19% and so on. So the rest seem to do just the same thing. The first one was showing percentages. This one shows the actual eigenvalue instead of a percentage. This one just changes the settings, but it's the same graph. This one shows the loadings. Again, I will not go into the loadings interpretation. I will try to run to the scores so that we can graph it. So now when we plot the scores, you can see clearly the benign, those who are classified as benign seem to be more on the lower score on the first principal component. Malignant one seems to score higher, but towards the positive side on the first principal component. The second principal component does not separate the two very well, but the first one does. So you can, it's possible to do some predictions using this. I did not run any of the classification algorithms, the k-means and the LDA on these two. So these red ones are the benign tumors and the black ones are the malignant tumors. So this quickly tells you that that set of 30 measurements can assist you in classification or diagnosis of a tumor. So the next one is the one we saw for images. Now we download the image from our website, the NASA website. That's what it's from NASA. And then we can display the image if you wish, the original image. This one is a bit slow. So when you look at the image, it's not easy to see that. You can see it's not very clear. There's a small pin that we had seen in the presentation, but when you look at the image, you can't see it clearly. So there's a lot of stuff going on. But at some point, we really restructure the image and we run the principal component. Now we can extract the colors that different colors that appear in the picture. If you want to do that, that is not of interest right now. But now we can separate the image into two, where different features of the image are picked up by each. The images take a bit of time to run, so they will load, but need to give them time. There, they have loaded. So if you look, I don't know if you can see it on your screens, but now the other thing you will notice is that the images are rotated. They are not the same direction as they were in the original one. So that happens sometimes when you're doing this, the images will be rotated. But the pin that we are looking for is around here. You can see a small dark spot, which was not easy to see in the original. So this is the outlier detection bit. And you can see that the first picture picks up the texture, the sand, because there's a bit of sand in the picture. It is picked up well by the first picture. And this one picks the darker colors and the shadows after separation. Again, there's more to explain, but I'm trying to run through this so that we can finish. I think this is the last one, the geochemical example. So this was some measurements taken from on limestone from some two formations in Nashville, Tennessee. I have given the website where I got this from with some more, it has some more explanation there. If you go onto that website, you'll get the full analysis for this. But for now, I'll just read in the data. So this is the data. This is what we shall use to categorize our data. This first variable is called the stratification position. So the geologists, if they're in the house, I think will be able to explain this better than me. Then there are all these measurements of these minerals. I think the first two are some isotopes. There's aluminum, there's calcium, there is iron, magnesium. Mn is what? Manganese, there's silicon. So these are all measurements taken on from all these positions, stratification positions from the two formations. So there will be some threshold which splits the two formations, as we shall see when we go through the code. So here we import the data straight from the folder. Oh, I'm repeating this again. You've already viewed the data. Then we pick up the the numerical variables, the ones that we need for the analysis rather. And we transform some of them to make the principal components run better. Sometimes principal components runs better when the data is symmetric. So sometimes when it is asymmetric, it may not work very well. So the transformation will assist in that and a few other things as well. So we look at the variances again. Again, you see some disparity. There's one of the variables. Why is a plot? So one of the variables seems to have a high variance, and that means we should do some scaling. So we'll run the principal components analysis. We pull out the scores. That's the new data, the transformed data. We can run the biplot. I will skip the biplot. we can plot the scores. Already when you plot the scores, I think I need to, let's plot the scores again. So when you plot the scores, you can still see some grouping. So there are some on the lower end, and then there's some that score on the higher end. Again, it's just the first principal component versus the second versus the first principal component. Now, remember the stratification position variable, we shall use 34.2 as a threshold to split them into two. So the ones that are less than 34.2 are classified as this Carter's formation and Hermitage. You'll get more this if you go. I don't understand the details of this stuff, and so let's do the stratification. So once we group them, we can now plot them using those groups and see if there's any separation. And when we do that, it's the same plots that we had earlier, the first and second principal components, but now we can see the separation. There's a bit of mixing because you have some blues that are mixed up with the reds. So when you see this, this might mean you need to go back to the data and find out whether this data, there's some errors in the data, or whether some samples were mixed up and so on. But clearly you can see that there's a separation between the Carter's formation and the Hermitage formation. There are also different ways you can classify. That is along this classification is along the second principal component. Along the first principal component, you also have some that score really low on this side and high. And if you go to the loadings will enable you to see the difference. So some of this is, I'll just run this classification that was done. It's already on that website. You can go and check. So because of the loadings and the chemical compositions that favor those loadings, you may be able to classify the ones that appear on this end as clay-rich limestone, and on this side as clean limestone. I think clay-rich are the ones that have more calcium. If you look at the loadings, calcium on the first component has a negative loading. It's more towards the negative end. So they are rich in calcium, the ones on this side, and the ones on this side are what? They have more of this aluminum, iron, and silicon. So I don't know what this classification means. Maybe the geologists, if they're here, they can assist. Then if you use the scores on the second principal component, you can classify them as dolomitized or non-dolomitized. I think this is a process where what do you call it? The limestone is converted to dolomite. But again, there's a lot of detail on the website that I've put in the code there. If you go to that website, you'll be able to see everything. So that's the last example. Everything has been all squeezed up. I hope it has made sense. Ideally, this should be a much longer class, going through several sessions to be able to understand the concept fully. But that is there are many other applications you can look at. These are the ones I prepared. So that brings us to the end of the presentation. And hopefully you can hear me.
Yes, Dr. And thank you for the presentation. I'm seeing a hand up from, sorry, let me just try to get this hand. And there's also on the chat, there's a question from Martin Mulinge. He's asking for detection on data structures. Should we use PCA or factor analysis, or both will do? Daktari, you're able to hear me?
Yes, I can hear you. Factor analysis is quite deliberate about finding the latent features. So if you're looking for latent features, I think factor analysis is a better model for you. But you may use PCA because factor analysis requires you to know how many features you're looking for beforehand. So PCA can help you to try to determine how many features to look for when working, trying to apply factor analysis. So you will have to understand both. You will need a bit of both when you're doing feature extraction. There are some very interesting examples from psychology. If you, especially when they were looking for the personality traits. There's some data. There's a very good example from the what you call sociology. Where they are looking for features, and they have many variables, so they're able to classify. The big five, the one I'm talking about, the personality traits, they were able to reduce them to exactly 5. Maybe you can look it up. It should be easily available on the internet. Look for the factor analysis in psychology, where they came up with the big 5 character traits. Was that the last question?
Yes, and there's a hand from Dixon Omucheni.
Dixon,
yes, I have a question.
Can ask.
There is a
yes.
I saw you did a PCA on some image, and if I looked at it, I saw it was a JPEG image. So I'm wondering, a JPEG image only has 3 channels: red, green, and blue. But you did a PCA on it, and then you were left with the two PCs, in which one of the PC was showing the pin. Maybe, I don't know, why did you need the PCA? Because the 3 channels, you don't need to compress them.
So what I did was the following. Let me see if I can get. Basically, what I've done is the following. I picked out, separated the channels. So if the channels, if the red was stretched out into one vector, one long vector, the green also into one long vector, and the blue into one long vector. So you ended up with basically 3 variables, but a lot of cases. So they're really long vectors, right? So now you have 3 variables, but so many cases. Now using those 3 variables,
is it a repeat of the same?
No, it's not a repeat of the same.
Photo.
No, it is
I'm
not.
I'm assuming that when the photo was taken.
Yes.
I'm assuming that when the photo was taken.
Yes.
It's a single image, right?
Yes.
Or multiple files of the same image.
It's the same image, but it has 3 layers.
Or a single...
So each layer is basically a matrix, right?
Yes, yes.
So you turn that matrix into a column, so that matrix becomes one variable.
Exactly.
And then you end up with 3 separate variables for each of the colors, right?
Yes.
So you run PCA on that new data set. Then it will try to get linear combinations of the same and give you them in order of importance. Now, if I run that same, I don't know if I can share, you will see that the 3rd component really has nothing much to show. So it basically separates them in order of importance. If you don't mind, I can share the R again and run show you what the third component is, because I picked only the first two. The third one will not show much because it will just be noise. Where is share? Where is the image? It's here. So there's a lot that's going on in between. I avoided running through that because of time. But here you can see we're picking the first and second. So if I pick the third, if I change this to the third one, you will see that the third one really is just does not capture a lot of information from the pictures. So you can see that, I don't know if you can see the screen.
Yes, I can see.
It almost has
Okay,
nothing.
so
Yeah.
okay, so does it mean maybe also when the third channel still has some information? Because if you look at it, you will also see its own some.
Yeah,
even though it's
it
noisy
picks up.
image,
It picks up different aspects of the picture, or rather, it's basically noise. So you can leave out the noise and just pick. I don't know if I'm making sense.
I couldn't
Let
hear
me
you
try to
clearly.
use some diagrams there.
Okay.
Can you hear me now?
Yes, I can hear you.
So basically, what we have done is this. You see, we have the image, but it is in 3 layers. So one layer is the green layer. We have RGB. So there are 3 layers.
Yes.
So this matrix here represents the red one. I reshape it into one column. So basically pick the first, because a matrix is, the picture is just a matrix. So you can pick the first row, run it down, pick the second row, put it immediately under that. So you end up with one long vector to represent, this is red, right?
Yes, yes.
So this is one of your variables. You do the same for the second one. You have one long vector, and do the third one as well. So you have 3 variables only, one for red, one for green, and one for blue. So you run your PCA on this matrix, right?
Yes.
So it will give you another set of variables, but now ordered in some importance, right? So this is the first principal component and the third
Second
one.
and third.
So this
I'll
is
be interested
converted
in
into
seeing.
then now this one, these 3 will contain different information about the picture. So we saw the first one picked out the texture, which was mostly the sand. The second one was picking out the darker colors, mostly the shadows. And that's where we're able to detect the small piece of metal that we couldn't see directly from the original picture. Then the third one doesn't have so much information. The third one is now the one I'm displaying here. So after you run this, you'll have to reshape this long one that you get now. You'll have to reshape it back into a picture. So you reshape it back from this long column into a picture, then we can view it. So that this is the one that was showing us the texture. And this is now like our first principal component, but now we have reshaped it back into a picture. And then there's the second one, which was picking up the shadow. Again, we've reshaped it back into a picture. So we have a first principal component and the second one. The third one seems to have nothing much for us. There's no useful information in the picture. It's mostly noise.
Okay.
I hope that makes sense. But if there are many other things you can do with the images as well. You can do compression. You can do, in this case, I was just trying to extract some outliers. So I hope this helps.
Yeah, it's fine. Fine. And then maybe, can I ask another question?
Yes.
Okay, you also showed some correlation matrices, and on one corner of the matrix were dots with the colors, and on the other side there were numbers. I'm trying just to understand, were those just a replication of the same numbers on the other side of the corner, assuming that a correlation matrix is symmetric?
It is symmetric. It's definitely symmetric, but if you want to look at the numbers, you look at the side which has numbers. If you want to, sometimes it's easier to visualize the correlations using the color scale instead of the numbers. So
could you just display?
So if we run one like this one,
maybe one, yes, for yes.
Like I need to clear these diagrams. Let me get the. So is this the one you're talking about?
Yes, this is the one I'm talking about, because I can see. So you are saying that these colors are actually the same values. They're actually just a coloration of the values on the left.
Yeah, you see on the extreme right, there is a scale, color scale. Scale will tell you the value as it gets, and blue, it means it's a high positive to dark blues, a high negative correlation as you go towards the dark brown. The lighter colors are lower values of correlation. So sometimes it's easier to visualize using the colors than to look at the numbers.
And
so the numbers do exactly the same
diagonal,
thing, but now they are graded using the colors. So
what
for
about
instance,
the diagonal?
Pardon?
The diagonal. Because the diagonal, you are actually putting some.
The diagonal would be a perfect correlation because
yes,
that would be a correlation with the variable with itself.
Yes.
So if you put the correlations there, you will just get one because it will be perfect, getting a correlation with the variable with itself. Now,
okay,
what we have used that diagonal to put in the variables. So for instance, if you want the correlation between this pH and L, you'll have to connect them here. Right? So it seems to be very low. It's about 0. If you want between this water holding capacity at 40 degrees and water holding capacity at 60 degrees, they're highly correlated. 0.9. So for instance, if you want the correlation between texture and this OHC at 60 degrees, oil holding capacity at 60 degrees, you can see it's 0.7. It's a bit high. So, and you can see this 0.9 is high. And if you go back to the color side, it's also dark blue. It's closer to 1.
Okay, I see.
So the same figures here are represented on this side, but using the color scale. So it's some people might find it easier to use the colors, and also the size of the circle tells you if the correlation is high. Both the color and the size.
I see. Yes. Okay, that's very nice.
Yeah.
Okay.
Okay. So I think that's the end of my talk. We I believe we have some. I've answered most of the questions.
Yes, Dr. I'm seeing 2 hands, but in the interest of time, maybe I could say that I'll share my email on the chat box for those who are interested in having further lectures on this. We can organize for a 5-day intensive session on this topic and also on R, so that we are able to understand and none of us is left out. So I'm sharing my email for you to be able to show interest so that you can organize a short course training, and also you'll get certification, and it will be in-depth learning. I don't know whether that will be able to sort us out, Dr.
Yes, we have run one short course already before. We did a short course, but that one was just on learning R. It's a short course offered through UNES. What was interesting is that we had mostly people from the medical health sciences as the participants. There were other people as well, but the majority seem to be from the health sciences. But anyway, we have the short courses which run through UNES. I think Gertrude will share her email, and they will be able to share more information on the cost and the dates when we shall offer them. So I think there's an email in the chat if you wish to take the short courses. We already did one for R. We had another one planned which has more weight on the statistics side and less on the R side. But if you were to do one which has more weight on the statistics, you are better off having done the one for R first, or maybe you should come already having basic knowledge on R. So this one was very compressed, so it was not very fair. It was very compressed, so time where we narrowed down to the details. Someone was saying something.
Oh, yes, this is Kamano. I wanted to say thank you for the presentation, and commend that effort. But I generally wanted to say that I think it's the right time that we should be going now computational as a department, and also the university fraternity. And yes, personally, I'm ready to take you through some of the aspects of data science. So when we have time, I think we can sort out for that. Then the last comment was about a series of questions, which was sort of like a pattern. PCA, as Dr. Katenda said, is an exploratory technique, especially for de novo analysis, and is not suited for all the problems, but is suited for problems where you like to explain the components that contribute most to the variance. And also it assumes that we can have, there exists a transformation which can lend highly nonlinear data into linearly separable scores. Yeah, what is called scores. So yeah, so there are other techniques that can also be applied for the same problem, but usually it's good to explore all of them for the betterment of subsequent downstream analysis, for predictive classification, or even for probably mutating variables into scores that explain the outcome of interest. Yeah, and somebody asked about multiple collinearity. So which are these highly collinear variables and how can you treat them? So PCA can help you determine that. Yeah, thank you.
So thank you, Kawanu. Kawanu is highly experienced in this data analytics. I think he's done quite a bit of work on gene expressions, if I'm not wrong. Is that correct?
That's correct.
Yes, this it's biological stuff. And I think someday maybe he can give. That's not the only thing he has done. I've also done some work with him, and it's he also is one of the people who inspired me to think more about data analytics. I am more of a pure mathematician, but this is a good thing for especially the students who always wonder whether you can, in what ways you can apply mathematics and so on.
Thank you. I'm glad I inspired at least one of my. Thank you.
Yes.
Well, can I comment something brief?
Yes.
There was a question that came up concerning a situation where the PCA is not able to handle the nonlinear data. And Dr. I think you mentioned that there are some other options. You can go for some other techniques that are able to deal with such data. Well, if you look of late, there is that proposal that we can also use other variants of the PCA. There are some PCA, some other PCA techniques that are currently these days oriented to even handling the nonlinear data.
Yeah, there is robust principal analysis, and there are some that work with regularization and so on. Yeah, there are more advanced principal component analysis that you can do. This was the basic one. You can do the robust, which is this first one is also very sensitive to outliers, and also very sensitive to the symmetry. If the data is asymmetric, you don't get very good results. So there's a robust principal component analysis, which can handle more adversity in the data.
Okay, and then in addition to that, actually, there are some other techniques we are experimenting with on our side. Like we have the supervised principal component analysis, and there's also a situation where there's another approach where it's proposed you determine the loadings of the PCA, and then later you apply a technique like the independent component analysis. So that independent PCA technique, it has also been said that it could be performing better than the classical PCA. So I think that one answers the question.
Yeah, there are situations where principal components analysis is sufficient. Independent component analysis tries to separate signals.
Yes.
And it's quite specific. Your signals should not be, they should be non-Gaussian. They should not be normally distributed. So when signals are mixed up, the independent component analysis is built. It actually tries to separate them. Principal components analysis sort of separates them, but in a half-hearted kind of fashion. But you have other methods that try to do the separation, like linear discriminant analysis. Independent component analysis is good for mixed, if you have a lot of mixed signals and you want to separate them. And some of the signals may be noise, and when you separate them, you're able to remove the noise. So ICA, though they all work with the basic, all of them boil down to singular value decomposition at some point. They're all connected by that.
Then for the sake of those colleagues in health research, there was an example you gave here concerning separation of malignant and the benign, I think, samples.
Tumors, yeah.
Yeah, sure. So in that case, it's normally advisable that even when you do the PCA of such data, you have to add a supervised constraint at the end, because
yes, that is correct, because I did not cover any classification techniques. This is exploratory in nature, and therefore can lead to classification. So now if you're going to do classification at that point, you can do supervised. You could use linear discriminant analysis to do some supervised classification. and you can do some cross validation to check the stability of your clusters and so on. So this is by no means complete.
Okay, sure. Then I think finally there was I think Martin, I think I saw Martin there asking about if you can use the PC and the factor analysis together. And I think it's okay because when you go to the factor analysis, as the name suggests, it looks for those latent variables. Middle books normally talk of the common factors. And when you do the rotation of the solution that you get, you are able now to see the separation in maybe of your variables. The problem with that technique is that you may end up having some factors that portray some kind of separation of your data, but it doesn't necessarily indicate to you if the factor represents noise. That's how the PCA comes in, because based on the split plot of the eigenvalues against the principal components, you can actually filter out the higher order principal components. So it's quite easier to actually have the components that explain much of the variance, and then you throw out the noise. So I think it's
also when working with factor analysis, you need to have a theoretical framework in place.
Okay.
So it doesn't work. The mathematical side can do anything you give it. It doesn't really care about the validity of the thing. So a lot of work in factor analysis must have a theoretical framework behind it first. So you don't do it before you have a theoretical framework behind it. What they normally call the domain experts. You have to be an expert in the domain with some theoretical framework before you apply the factor analysis method. So you.
Okay, thank you.
Can I ask my question?
Yes.
Now, if the influence of your factors are spread through 3 components, because
Yes.
I've seen you are using 2 factors for the principal component 1 and 2. Now, if it is spread up to the 3rd one, do you have a visual representation that can bring a 3D to take care of the 3rd influence
Yes,
of the 3rd component?
Up to 3 dimensions you can draw. The only problem with 3 dimensions is you have many different views. Unless you have if you can do it in MATLAB you can visualize 3-dimensional graphs much better than in R. But yes, it's possible. Sometimes it's better to have more than one tool in your bag. So you can take the data into a different software and visualize it better. But in 3 dimensions, you have too many different directions to look at. In 2 dimensions, and more often than not, the 2 dimensions are sufficient for visualization and detection of the patterns. But if you need, there are some analysis where you need, like if you are doing image compression, you could take as many as 100 dimensions, or even 20 or 30. Those ones you cannot, there's no way to graph them. But the theoretical framework holds even beyond 3 dimensions, so you can still work with them, but you're just not able to graph them.
Okay, thank you.
But for 3 dimensions, you can do it. It's basically a 3-dimensional space. That one you can graph. What you cannot graph is anything beyond 4 and beyond.
Maybe I can comment about it.
Yes.
Well, you can have the 3 dimensions like we have suggested, especially in MATLAB. But finally, if you have to interpret the correlation loadings, you have no option. You have to go back to the 2-dimensional approach so that you're able to interpret the negative and the positive loadings. So for 3 dimensions, it's good there for observation, the visual observation. But when you come to the interpretation of the loadings, you really have to go back to the 2-dimensional approach.
So the other thing about the 2 dimensions is it's not always the first 2 that are the best for your work. Sometimes the first 2 may not contain the information you're looking for. So you may have to go further and plot 2 other dimensions that are different from the first 2. Because there are sometimes that you may find the lower dimensions give you more information about the separation, especially when you're doing classification. Sometimes you may have to use, you may find more structural information in other dimensions other than the first 2. So you have to do a lot of exploration mostly.
That is good information, because we have always thought that you must take the first and the second components.
The first and the second components contain the most variation. They can explain the most variation in the data, but sometimes they do not contain information that can help you to classify. Sometimes that it's not always the case, but you may have situations where you need to use, or rather you'll still find more information in other principal components that have less variation, but can still pick up they're able to separate, do some separation, and therefore can lead you to some kind of classification.
Okay, thank you.
Thank you, Daktari, and thank you everyone for participating. I believe, I know we may not be able to answer all the questions, but I've shared my email. You can show your interest and we'll be able to organize a short course for a more interactive activity. Dr. Katende, any final remarks?
Thank you very much for showing up. I was impressed by the turnout. We have, I thought we would finish by 11, but the questions were many. We've tried to answer as many as possible. But if you are interested in having a more long form kind of setup, you could get in touch with Eunice about the short courses available. But we can also arrange for another presentation on some other techniques as well. And Dr. Kamanu was also offered, I think, to give a presentation on what? On this data analytics and techniques. So maybe we shall organize for him to give. He has some very cool stuff.
Yeah. Okay.
So thank you. I think back to you, Gertrude.
Thank you all, and I think we'll end it here, and we'll be sure to share any further webinars on the same. Yeah, thanks so much, and have yourself a good afternoon.
Thank you.
Thank you. Bye. Bye-bye, all of you.
Thank you and bye.